So I want to walk you through the concept behind Gabriel's horn and some of the mathematical calculations that go into this, just because I think it's a really cool thing to see, and conceptually it plays with a lot of ideas like infinity and a visual picture and how you play with that. So I just want to show you how that works. Now before we go into that, I want to explain a little bit about what I'm recording this on, because I think it's kind of funny. But my phone is sitting on top of a wheat-thin box that is duct taped to a step stool. That step stool is on 2 stacked chairs and it is threatening to fall over. So if there's a little edit, bit in this video, it's because that probably fell. So let's go ahead and get down to this. So Gabriel's horn. Now this applies to the function 1 over x, which we're going to end up having 1 over x squared, but I want to show the progression of this. So let's go ahead and draw up a graph of this. So we have our x and y axis, and this is for f of x equals 1 over x. And this is what we're going to be working with here. Now, that graph looks something like that. And we know that, well, if 1 is divided by 1, it's going to be 1. If 1 is divided by 2, we're going to have 1/2. So we're getting a progressively smaller number. Now, here's what we're going to do. We're going to evaluate the area under this curve, and we're going to evaluate that from 1 to infinity. So we want to find how much space is under there. So what we're going to do for this is we're going to use an integral, because we know an integral is essentially a Riemann sum of all the little rectangles under that. It's just as that number of rectangles goes to infinity over that interval. So this can be written as the integral of 1, because that's our lower limit, to infinity, which is our upper limit of our function, over x dx. And that's our change in x, basically. I'm assuming if you're watching this video, you know a decent amount about calculus. So I'm going to kind of skim over a lot of the explanations of this stuff. It's the principle that I want you to see in this, not the actual calculations so much. So this is what we've got. Now, normally we'd say, well, the integral of 1 over x is natural log of x, and then we'd, well, plug infinity in for x. We'd subtract 1, a natural log of 1 from x, and that would give us, our area under the curve. But that doesn't really work, because infinity is not necessarily a number we can run calculations with like this, because it's an indefinite form. We don't know if infinity plus infinity is a different amount of infinity or what. It's infinity. So we can't use that in a calculation. But what we can use is something plugged in place of that. So what we're going to do is we're going to say, well, we're going to write infinity as being as b, and then we're going to take the limit of b as it approaches infinity. So what I mean by that is that we can rewrite this as being the limit of b approaching infinity. And now we're just going to plug in our integral. So we have of the integral 1, but we're going to replace infinity with b. And then we're going to write everything the same. X dx. So now let's go ahead and solve this, because this is in a form that we can solve and evaluate. Sort of. You're going to see what happens here. So, well, this is going to be the limit of b approaching infinity of natural log. Natural log, and I'm going to skip a few steps here, and I'm basically going to say it's the natural log of b minus the natural log of 1. My handwriting's not great, I'm kind of going downhill there. But let's look at this conceptually. Well, natural log of 1, we actually don't have to worry about that because of what happens here. Well, if we're going to plug in infinity for this, what happens? Well, if you take natural log of a progressively larger number, it's going to actually blow up your answer. You're going to get progressively bigger and bigger and bigger. Now, it's going to happen very slowly, but ultimately, the natural log of b, as b approaches infinity, is also going to approach infinity. That means that infinity minus anything is just going to be infinity. So this is an indefinite form, which we would describe this as being, I'm just blanking on it. Well, it's diverge. So if the function goes to a point, we'd say converge. This function's going to diverge, which means we don't have a specific point we can evaluate. So this can't be solved. Now here's where it gets fun, and this is what's I think is so cool about the Gabriel's horn thing. So I'm going to leave a little of this up there. Now let's look at this a little differently. Let's say we want the volume of a rotation. Now volume rotation, we're going to use the function because we know, well, this function evaluated is that. And we're going to write that line as being the radius of a cylinder. So it's also going to go to there. And that means we're basically going to have another thing here, like that. And we're going to be rotating this around the x-axis. So we're going to get a horn-shaped solid shape. And that solid shape has volume. And you can kind of see the horn shape there. So assuming that this is our radius, our function equals our radius, we're going to use the method of cylinders, which you probably are familiar with. So we're going to have pi r squared height. That's our volume of a cylinder. So we're going to have pi. We're going to plug in our function, which is 1 over x squared, times our height, which is going to be delta x, change in x. And 1 over x squared, we can simplify that down to 1 over x squared. Now, I'm going to go ahead and erase this, and we're going to set up an integral that will use these concepts. So, what do we have here? Well, we've got, first off, our integral, because this is going to give us our area, and we have it from 1 to infinity. And these are the same limits of integration we used on the last one. And now we're going to plug in our new function, which is our function of rotation for the volume. So we're going to have pi r squared, which we now know is 1 over x squared, and dx, which is our change in x. dx. Now let's watch what happens, and this gets kind of cool. So we're going to do this exact same thing. So we're going to rewrite this as being the limit as b approaches infinity of the integral of 1 to b pi. I'm going to stick this in parentheses just for clarification purposes. dx. Well, let's keep going with this. Now, we can pull out pi because it's a constant, and we can evaluate this. So I'm going to skip a couple steps here. We're going to say the limit as b approaches infinity of pi, integral of 1 to b, and we're going to write this as being negative x to the negative 2. So that's negative x, negative 2, dx. Well, we're going to go on to solve this integral, and you really don't have to worry about that thing a whole lot, because that's just going to stay there. It's just defining what b is. So nothing has to get done with that in our integral. So this is going to wind up giving us the limit b approaches infinity, and our integral 1 to b. Oops, we actually don't need to do that. I'm going to skip a few things here. We can go ahead and actually solve this. So you know that this is going to be that plus 1 over what we have, basically our rules of integration here. So we're going to get pi negative x to the negative 1, and this whole thing is evaluated from 1 to b. I skipped a few things because I'm assuming you probably know how this works. Well, now we can evaluate this. So, this whole thing so we've got the limit b approaching infinity of pi, and we're going to now start substituting things in. So we're going to have negative b to the negative 1, and then we're going to have that minus that. So it's actually going to be plus, because we know minus. I'll go ahead and write out that whole step so you see it. Minus negative 1 to the negative 1. Well, now we can start solving this. And this isn't too bad to do. So, because think about what is b to the negative 1. Well, this, we can rewrite this as being 1 over b to the 1. So if you think about, well, that negative, what's b? Well, b is going to infinity. So 1 divided by infinity approaches 0. So that term is 0. I just wanted to clarify that for you guys. And then what's negative 1 to the negative 1? Well, that's 1. So we wind up with 0 plus 1. So now we've got 1 times pi, which just equals pi. So the answer to this is pi. That's the volume of this horn-shaped solid that we get. So I find that really, really cool. Now I'll explain kind of why we can make this assumption about the volume, but we couldn't make that assumption about the area. And this is a conceptual part here. So this is our graph. And I'm going to draw the graph of 1 over x. So 1 over x. Which kind of looks like that, ish. Now I'm going to draw 1 over x squared. And well, we know that, if x is 2, then we're going to have 1 over 4. And if x is 4, then we're going to have 1 over 16. And the thing in here is that it's decreasing much, much quicker. So this whole thing ends up looking kind of like that. Now, think about what infinity is. Well, it's going in, we're getting a lot of area. Both of these lines just keep going forever. But the area under x, 1 over x, well, there's still a decent amount of area here. It's decreasing, but it's not decreasing very fast. So there's a measurable amount of space. But 1 over x squared, well, that kind of changed really quickly. And there's a minimal amount of area here, and this tiny amount of area goes on forever, but it's not a measurable amount. That's why we kind of, in a way, it just stops at a certain point. There's no more under there. And it does that both directions. So we can calculate the area under here, because this is such a small amount it doesn't matter. We can't under here, because this keeps going to infinity and it does matter. And that's just, for me, something that's kind of fun to try and wrap my mind around. And I hope you had some fun watching this video. I get very enthusiastic on things like this, so I don't know that I explained it particularly well, but just the idea and kind of thinking about this is what I want you to take away from it. So if you have any questions, go ahead and shoot me a comment. If there's any other problems you want me to work through and try and explain, if you actually have questions about like a specific type of calculus related or any other kind of problem, honestly, let me know and I'll try and do a video on it to the best of my ability, explaining it, nicely and simply so you can have an example to work off of with other problems. So, hope you have a good day and see you next time.